In this video, we will discuss linear programming problems. But before we proceed to actual OR linear programming problems, let us discuss what a linear problem means. Linear means that all the variables in a mathematical function have a degree or index of 1. Another way of saying this is that a variable x is related to another variable y by means of a straight line. For example, x plus y equals 2 is a linear function that can be illustrated as such. Now, the variables in this expression can be more than 2. For example, x plus y plus z equals 2 is also a linear function. Some other examples of linear functions include x by 2 plus 3 equals y, 2x minus 3z equals 1, 4m plus 3n equals 5p, and so on. Note that regardless of the dimensions, that is the number of variables involved of the expression, each variable or even a term of unknown has a degree or index of 1. This is in contrast to functions such as x plus y squared equals 1 as shown in this figure. Note that the degree or power of y in this case is greater than 1, and as shown in the figure, x and y are not related by a straight line. Similarly, functions of the form e raised to x, known as exponential functions, log x, known as logarithmic functions, and other such functions are also not linear functions. In the same manner, xy minus 1 equals 0 is also not a linear function, as the term xy is a multiple of two variables, which makes it nonlinear. Its graph is something like this. And as you can see, this graph is not a straight line between x and y. This can even be proven mathematically if you just rearrange the equation as such. And as you can see from this expression, the degree or power of x in this case is -1. So how is all this related to linear programming? As the name suggests, linear programming problems are planning problems where the mathematical model is composed of only linear functions. Linear in this case refers to the requirement of the model having all linear functions, while programming in this case refers to planning. So linear programming essentially is the planning of activities to obtain an optimal result among all the feasible alternatives. The most common type of linear programming problems are resource allocation problems, where we attempt to maximize the profit of business, for example, or minimize the cost of production, for example, while being subjected to certain constraints or limitations. The limitations in such cases would be, for instance, the availability of raw material or availability times of production resources such as machinery and so on. Another type of linear programming problem is the trade-off between costs and benefits, where we attempt to maximize the benefits by minimizing the cost. Recall the key components of a standard OR problem. We had some decision variables, x1, x2, and so on, until xn, which is the number of decisions that we had to make. We had an objective function, which we wanted to maximize, that is, find the maximum value of, or minimize, that is, find the minimum value of. We had certain constraints under which our model was supposed to operate, and certain parameters that were used in constraint formulation, and so on. Now, a standard linear programming or LP model follows this standard OR model. So in the standard LP model, we have some resources, or M amount of resources, such as money, equipment, vehicles, personnel, and so on and so forth. We have certain activities which we are supposed to perform and based on which we need to make decisions. And these are N activities corresponding to the N decisions that we need to make. Examples would include production, investing, advertising, shipping, and so on and so forth. We have the level of each activity for which we make the decision for this activity, and this is represented by xj, where j in this case would be 1, 2, all the way up to n. Examples of this include the production rate or usage rate. And finally, we have the overall measure of performance, which is our objective function z. And this could represent the profit, cost, time, and so on and so forth. Let's consider an example. Suppose that I run a drink stand outside of an office building and I sell just two types of drinks, coffee and tea. And every morning I bring a limited amount of resources, which are the raw materials for coffee and tea. Let's try to identify some of these raw materials. Now, this is a hypothetical example, so I'm not going to be exhaustive. But just to give you an idea, let's consider some basic resources, such as ground coffee. So let's say I bring about 200 grams of ground coffee, 100 tea bags, 100 grams of sugar, 100 grams of cream, and 5 liters of water. So these become the maximum amount of resources that I have available for the day. And I can use these to make some cups of coffee and some cups of tea. So if I count these, I have 1, 2, 3, 4, 5 resources. So in this case, my M becomes equals to 5. Now I need to do one of two activities. I either need to make coffee or I need to make tea. So the total number of activities that I can do is only 2. So N becomes equals to 2. Now, how much coffee I make or how much tea I make is the level of each activity. Let's say X1 represents the number of cups of coffee I make. So X1 would be equals to the number of cups of coffee. And X2 would be equals to the number of cups of tea. Now, comparing it to the standard OR model, this X1 and X2 are our decision variables. So in this case, we need to make two decisions, which are given by the number of activities that I have. Now, I have 5 resources, and a certain amount of each of these resources is going to be used in making the coffee and tea. So let me just give you an example of just one resource. So let's say that a cup of coffee is bigger than a cup of tea. So a cup of coffee can hold about 350 ml of coffee, and a cup of tea can only hold about 250 ml of tea. That means that a cup of coffee would require 350 ml of water, and a cup of tea would require only 250 ml of water. So this total amount of water that is utilized in making the coffee and tea should be less than the amount of water that I have available, or it can be equal to that as well. So if I write this mathematically, it would become something of this sort. This is what is known as a constraint. Note that the 350 ml here is changed to 0.35 and the 250 ml is changed to 0.25. This is because of the requirement of maintaining dimensional consistency, which states that I need to maintain the same units on both the left-hand side of the constraint and the right-hand side of the constraint. So as the maximum resource in this case is in liters, I converted all these milliliters to liters by eliminating this suffix m, which represents division by 1000. I can also do the opposite. That is, I keep the left-hand side as milliliters, and I convert these liters into milliliters by multiplying by 1000. Either way, whichever approach you use, just make sure that the units of the left-hand side and the right-hand side are equivalent or the same. Now, coming back to this expression, this means that 0.35 liters per cup of coffee times the number of coffee per day, which would give the total amount of water used in making coffee for the day, plus 0.25 liters per cup of tea times the number of cups of tea per day, which would give the total amount of water used in making the tea for the day, must be either less than or equal to the amount of water that I have available, which is 5 liters in this case. So this is one constraint. In this way, we can make a constraint for each of these resources. And in essence, each resource will have its own constraint, because if any one of these resources is depleted, we will not be able to make the finished product anymore. For example, if we run out of water, then we can neither make tea nor coffee anymore. Similarly, if we run out of tea bags, we can no longer make tea, and so on. So the number of resources that we have is going to specify the number of constraints of our problem. Finally, the overall measure of performance of our problem is the maximum profit that we can make by selling the coffee and tea. This will be our profit function, or in generic terms, our objective function. And in this case, we want to get the maximum profit. So this is what is known as a maximization problem. And it's also a resource allocation problem, because essentially we are trying to identify the best mix of these resources to sell the maximum number of coffee or tea so that we can get the maximum possible profit. Now, LP models have a fairly standard structure. As we stated before, the resource allocation problems are the most common type of LP problems that we face. But these are not the only types of problems that can be represented as LP models. In those cases, we make use of this extended model, which is shown on the right over here. Now, resource allocation problems involve allocating scarce resources necessary to complete certain activities to those competing activities. Now, each LP model follows the structure, where we try to identify the problem that we are going to solve, whether it's a maximization problem, which is maximizing the objective function, or a minimization problem, which is minimizing the objective function. And based on this, we call it a maximization problem or a minimization problem. Then we specify the restrictions or limitations that govern our model. These are called as functional constraints. If you focus on the resource allocation problems, you can see that all functional constraints are of the type less than or equals to. This is because the maximum amount of each resource that we have available is given on the right-hand side of the inequality. And on the left-hand side of the inequality, we have the utilization of this resource. In other words, the total amount of resource utilized, which is given by the left-hand side, must be less than the total amount of resource that is available, which is the right-hand side. Hence, this is where this less than or equal to inequality comes from. The last line of the constraints is what is known as the non-negativity constraints. This implies that an activity or decision must be numerically greater than or equal to 0. For example, the number of cups of tea I produce in a day must be either 0 or greater than 0. That means that I cannot produce -1 cups of tea per day. This is the standard format for a resource allocation LP problem, but not the only format. We can have minimization problems. For example, the minimization of the damage done to an organ during radiation therapy. This is also an example of a cost-benefit trade-off problem, where the cost is the damage to the organs due to stray radiations, and the benefit is the benefit received during radiation therapy, for instance, as a cancer remedy. In the extended model, we often see a mix of equalities and inequalities, as shown here. This is a less than or equal to inequality, which is the same as that found in the resource allocation problem. The second inequality is what is known as a benefit constraint, and there may be a number of such constraints in a problem. Benefit constraints specify the minimum level of benefit that must be received, or that is essential, on the right-hand side of the inequality, while the left-hand side specifies the possible amount of benefits we can receive from all the activities combined. So intuitively, this constraint can only be satisfied if the combined benefits from all the activities meet the minimum amount of required benefit, at least, or exceed them at best. In other words, the combined benefits should be at least equal to the required benefit or greater than it. Then we have equality constraints, which specify that the left-hand side must be equal to the right-hand side. And finally, such models may also eliminate the need for non-negativity constraints, making the level of activities to be unrestricted in sign. That is, the level of activity can now be negative as well. This is a list of the different symbols used in the model and their description. Z represents the objective function, which is again the value of the overall measure of performance. And as shown in the previous slide, we often write Z in the form of some parameter times the level of activity, and so on and so forth. And Z is a combined value of all these terms. xj represents the level of activity or the decision that we have to make for activity j. If we properly define the decision variable at the initial stage of the problem, the modeling for the rest of the problem becomes relatively straightforward. Hence, choosing the decision variable is essentially the first step of a model. Cj, which is used in the objective function, represents the increase in performance z that result from each unit increase in activity j. Bi is the amount of resource I available for allocation to activities, and this is usually given as the right-hand side of the inequalities or equalities in functional constraints. Finally, Aij is the amount of resource I consumed by each unit of activity j, and this makes up the left-hand side of our functional constraints. This is how we can represent the LP model in the form of a table, where the resources are listed on the left-hand side, the total amount of resources are listed on the right-hand side, and the resource usage per unit of activity is given in the middle, here in the purple block. And we can identify which activity we are representing by this block given in red. Finally, the contribution to z per unit of activity given by the parameter cj is written at the bottom. This is the tabular representation of the LP model.